someone to be kind enough to solve that?
So the first time you used Faraday lens and the second time you used Ampere?
Yes.
When you're doing that A plus B plus C plus D, how do you know? Because last time it was A and C, now it's B and D. Like, how do you know which one's cancel out?
It's the ones where
They're all parallel technically.
DL is perpendicular to the magnetic field. Because DLA is a vector like that, DLB is that way, DLC, DLD.
So D and like this, you said.
Yeah, so magnetic field is going up where I just do my
Oh, okay.
Amperian loop. And so that's why, and this, just because of the way I labeled it, those two, DL was perpendicular to the magnetic field.
The other time it was A and C.
Yes.
Okay.
All right, what do we get?
2.99 times 10 to the 8.
Units?
Meters per second.
And so what we have here is a number incredibly close to the speed of light. So Maxwell jumps to he proposes that because the speed of the electromagnetic wave is so close to the experimental values for the speed of light, he speculates that light might be an electromagnetic wave. And that is sort of a major piece of physics there.
That's cool.
But it then, yeah, it is actually. And then, so this is 1870 or so. Physicists look at this and they said, wow, that's incredible, but there's a mistake. What I'm asking you is, what mistake is there? Or what perceived mistake is there?
He's making an assumption that he.
Yeah, you're connecting the speed of light just because it looks like close to the speed of light. You're saying it is the speed of light, which is.
That's not the issue that physicists had.
I was gonna say that's assuming it's in the vacuum of space, permittivity, free space. That assumes that if it's somewhere in not free space, it's no longer
All right, so let's assume it's in free space. They said, the physicists at the time, Lorentz being a big proponent of there's a mistake here. And Lorentz spent the next 30 years jumping through hoops trying to justify it. All right, so his speed there, even if we don't want to connect it with light and just say it's speed of an electromagnetic wave, they're still gonna, physicists still looked at it and said there's an issue. All right, so how fast are you moving right now?
whatever
Depends on your
the Earth
reference
is
point.
rotating
Depends on your reference point.
Where does the reference point play in this?
There is no reference point.
That's the issue that physicists had. There's nothing in here that says relative to what. And so, if Maxwell is to be believed, then the speed of light would be the same regardless of who's observing it.
Yeah, regardless of the reference point.
Yeah.
What's
That'd be-
the issue then?
The issue, it'd be as if a car's coming towards me and I'm standing on the side of the road, the car's going 50 miles per hour relative to the road, then to me it looks like it's going 50 miles per hour. If I'm in a car heading towards it, going 25 miles per hour, and we're going for a head on, he's going 50 miles per hour relative to the road, I'm going 25 relative to the road in the opposite direction. From my point of view, he's going 75 miles per hour. Well, if this is true, then it would be the equivalent of that car's going 50 miles per hour regardless of how fast I'm going. Now, in terms of speed of light, that if I'm traveling near the speed of light in the direction it's traveling in, it still looks like it's going almost 300 million meters a second. If I'm heading towards it, it still looks like it's going 300 million meters a second. If I'm standing still, it still looks like it's going 300 million meters per second.
You know how the speed of light always is though?
Well, this was the issue that the last 30 years of the 19th century. Then Einstein comes along and says, well, let's suppose that there's not a mistake.
Yeah.
The speed of light is the same.
And it's the limit, and it's like the one thing that we can say doesn't need a reference point.
Yes.
Because time is your reference point.
So, if this is correct, so 1905 pops up, Einstein produces basically four papers, three of which could all probably made him deserving of a Nobel Prize.
Is this the photoelectric effect too? Does that lead into that?
Photoelectric effect was,
Electromagnetic waves?
photoelectric effect I don't think was, so it was special relativity, general relativity, the basis, the foundation of general relativity, showing that, coming up with evidence of the particle nature of atoms, and the fourth one I can never remember. Photoelectric was not there yet. In the end, he got a Nobel Prize for contributions. Generally attributed to his being Jewish, and the Nazi Germany did not pop out of the vacuum. The anti-Semitism was there. All right, so if the speed of light is the same regardless, propose the following thought experiment. I have a mirror here. I have a box that is traveling, so this will be the lab frame. I'm looking at it from the side. The box is moving at some speed v. It shoots a light up. There's a horizontal component, so the light should hit the mirror, come back down, and get to the box. So the box basically is traveling a distance v and some time t. If I'm in the box's point of view, so the box frame, I'm not moving at all. The light goes up, it comes back down. This distance here, we will make h. And so now I just have to figure out the, well, in essence, time it takes. So I know the speed of light, we'll use the letter C. The speed of light is going to be equal to distance over time. So in this case, the distance it travels is 2h, and the time, I'll just put t sub b for a box. And I'll put t sub l for a lab. Up here, the light is traveling, let's see, well, this distance would be half of vt, so half of vtl, that's h, and so this hypotenuse would be the square root of h squared plus 1/4 v squared tl squared. So here, the speed of light would be 2 times the square root of h squared plus 1/4 v squared tl squared.
So just distance formula?
Yeah.
Oh.
Over t sub l. So if the speed of light is the same regardless of the reference frame, then both of these have to be true. So let's, I want to solve for h and then plug in, because h is an arbitrary value. So h becomes 1/2 CTB. Plug that into that equation. I'm going to go ahead and multiply by TL and divide by 2, so I get 1/2 CTL equals the square root of 1/2 CTB squared plus 1/4 B squared TL squared. Square both sides, we get 1/4 C squared TL squared equals 1/4 C squared TB squared plus 1/4 V squared TL squared. This is supposed to be a B. Multiply everything by 4 to get rid of those. And now it's just a matter of trying to get it into a form that looks good. So what I'm going to do is I'm going to solve for TL. So I'm going to bring this over. So I have C squared TL squared minus V squared TL squared equals C squared TB squared. Factor TL squared out of that. What I'm doing is at this point deriving it to get it into the more traditional form. Actually, I'm gonna divide by c first, c squared, so I add, and factor out TL, so I have TL squared times 1 minus v squared over c squared is equal to tv squared. So all I did was just factor TL squared out and divide it by c squared, or vice versa. So TL squared equals TV squared over 1 minus V squared over C squared. Take the square root. And so the time in the lab frame is equal to the time in the box over the square root of 1 minus V squared over C squared. So if the speed of light is constant regardless of the reference frame in a vacuum, time's not the same. The assumption up until here, up until 1905, amongst the knowledgeable physicists, everyone else was a crackpot if they believed this, that time was not the same. Matter of fact, some of this stuff shows up so often that they started coming up with abbreviations. So first, for example, V over C, often beta. If beta is 0.6, you're traveling at 0.6 times the speed of light. 1 over the square root of 1 minus beta squared, because that's all. That's gamma. This is known as the Lorentz factor. Now Lorentz gets credit. Lorentz did a whole lot of the mathematics that we'll be using. He just refused to take that final leap of assuming that the speed of light was constant regardless of the reference frame.
Oh, there goes the Nobel.
Pardon?
There goes the Nobel.
I think he won it for something else.
Oh.
He was a rather well-known, powerful physicist in the field. And so we can write it generically as that time is equal to what's known as the proper time, gamma times the proper time. Proper, when you see proper, that is the zero movement reference frame. In this case, the proper frame is the box, because the box is not moving. If we're talking about time passing in the box is not moving. That's the proper frame.
So if the box is not moving, then what is that?
In the box frame, the box isn't moving. Just like in your reference frame, you haven't moved at all. The world has moved around you.
This is also a good point of why we can't move faster than the speed of light, right?
And this is the evidence that physicists bring up of why we can't go faster than the speed of light.
Because it would make it zero, it would make it negative under the square root.
Yeah, or actually, if we hit, I should amend that, we can't, if we start out slower than the speed of light, we won't go faster. Because as soon as we hit C, we end up with 0 on the bottom, and the mathematicians haven't figured out how to do that yet. But it does allow, actually, for something starting faster than the speed of light that will never go slower.
What?
You end up with an imaginary, from what our point of view is, you end up with an imaginary or complex time. But it's not zero or infinite. It is defined mathematically. Now the question is, what does imaginary time mean? Now,
You mean time as a complex number?
yes.
Oh, okay.
So, and the particle that the theorists have come up with, or a theorist came up with, is the tachyon.
Oh, I see, because then you would have a negative under the square root, and that's where your negative, or your complex number comes from?
Yes.
Okay.
And the trouble, if we ever find a tachyon, I think have to redefine what time is.
Oh, that's where the tachyon comes from?
Yeah.
Oh, I thought it was just something that somebody made up, at some point to
Well,
say something, a particle that moves faster than light.
It basically, a physicist came up with that, worked out all the math. You know, if you're in a publisher parish atmosphere, then, you make stuff up.
So there is math behind the tachyon?
Oh, yes. Yeah, yes. The trouble is, if I shot you with a tachyon gun, you would be, based upon our knowledge of time, you would be hit by the tachyon before it pulled trigger.
Yeah.
And so this is a little bit mind bending. So I'm not quite sure how you would actually find it.
Is it because time's not linear? Or like our perception of time isn't linear?
or to me, that's a tricky question because I really couldn't tell you what time it is. Nor do I think physicists really can tell you what time it is.
Is this where like the theory of relativity starts?
Oh yes, this is special relativity right here. So the fact that time is not the same, is it linear? If you're in a non-accelerating frame, then time is still linear, just it might be progressing at a different rate for you as it is for someone else. Part of the implication of this is if you're late to school and you're speeding to get here, your time will slow down.
See, it did work.
Now, perceptibly? Probably not. At what point do we really, do the relativistic effects kick in? When is the Lorentz factor big enough to matter? Typically, in physics, when the Lorentz factor gets to 0.1, that's when you start taking relativistic effects into account. From a practical point of view, GPS satellites are traveling well below 10% the speed of light, but they still take it into account. If you don't take relativity into account, I think GPS satellites will be off by 30 meters a day. They'll slowly get off by that much.
Pretty powerful stuff. It's pretty powerful stuff.
It is. It is. The trouble is, this is 1905 he comes out with this. In 1905 he comes out with the framework of general relativity, which deals with accelerating frames and more gravitational stuff. 1918, somewhere in there, is the first evidence that general relativity is true. There's no evidence of special relativity being true, of any of this being true, until we get to 1940. And then
You have like quantum mechanics being developed like simultaneously too, sort of.
it is, special relativity started just a hair before it, but by 1920, both of them are basically physics.
Oh, I was just wondering, because you can't reconcile it with general relativity, right, yet, so, but they were both being developed at the same time, like, is it like different paths that were like?
Yeah,
being developed?
Einstein was never really a believer in interpretations of quantum physics.
What do you mean?
As in, there's a certain randomness to quantum physics that I can do the same things twice and get different results.
He didn't like that.
He did not. That's the expression, God does not throw dice. He felt that if we don't know what's going to happen, that's one thing, but that means there's something else there that we just haven't figured out yet. And quantum physics, the interpretation is there is a randomness to it. That it's not that there's not the hidden variables, it's the fact that it really is random at some level. So Einstein was not a fan of that.
And I was not a fan of randomness.
Right.
That's those no pill. You gotta know it.
So this is the point where when I first started here, we would launch into special relativity. However, it did skip something. After the first couple of years, one of my students ended up going to NC State, and he said it really would have been nice had we done AC circuits.
What circuits?
AC.
Oh,
We've done AC. And so then I started incorporating AC circuits into it. So we are going to put special relativity on hold, and then we'll come
through
back.
all of that, and then we're just gonna be like, oh, okay, let's go to something else.
I got 3 minutes left, and I'm going to explain general relativity as best as I know it. General relativity, the course that kicked my butt. So, I think I've mentioned the first test, general relativity. My goal for the first test was to understand the question.
Yeah.
I did not succeed.
Dr. Fox.
Yes.
On Blackboard, chapters 33 onward are unavailable.
To you?
I mean, if anybody else wants to check, but to me,
All right, thanks. I'll
Yeah,
try to remember.
33 and
Okay.
34 are unavailable.
I'll check. All right. Einstein proposes that if there are two situations for which there's no way to experimentally tell the difference, then there's no difference. Not whether that we have the equipment to experiment, even with the equipment, we can't tell the difference. So he proposes, if I am in a box that is launched through space, I can't see outside, launched through space and accelerating at some rate of similar to the acceleration of gravity. If I shoot a light across here, it's not going to hit directly across because this thing is getting faster and faster, so what the light should do is it should actually hit below where it started. Or it hit below at a lower height as this thing gets faster and faster. If I were on a planet in a box and the acceleration of gravity was little g, there's no way actually to tell the difference between being in a box accelerating through space with that acceleration or being on a planet with the acceleration of gravity being the same amount. So he proposes that since there's no way to tell the difference between those two, that being on the planet should cause light to also curve. And so this gets into the general idea of the fact that mass itself causes space to curve. If mass causes space to curve, then if I have a huge mass, let's say for example the sun, it should cause space to warp around it. Now, it's very difficult to tell this if I'm looking at it, because, well, you'll go blind. So, but there is one point every couple of years in which you can do this, in which we just happen to be in the right spot with the right size moon to block out almost the entire sun during a solar eclipse. During that time, the theory is, general relativity is true, that if I have a star on the opposite side, the light from the star should come along, it should curve around the sun because space is curved,